Well, good morning all, and thank you very much for being here. I'd like to welcome you to this morning's SEAM webinar on Thursday, the 12th of August, 2021. SEAM is, of course, the ARC Training Centre for Surface Engineering for Advanced Materials, located at Swinburne University of Technology in Hawthorn, a suburb of the city of Melbourne, Australia. My name is Dr. Thomas Pattison. I'm a postdoctoral researcher here at SEAM, and I'll be moderating today's session. Before we begin, on behalf of everyone located here at SEAM, I would like to respectfully acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional owners of the land on which Swinburne's Australian campuses are located in Melbourne's east and outer east, and pay our respect to the elders past, present and emerging. I would just like to remind everyone to please feel free to post any questions or comments you may have for our presenter today in the chat during the session. Myself and my colleagues will be looking through them, and time dependent, we'll ask them of the presenter and we'll have a little Q&A session at the end. Now, it's my pleasure to introduce our speaker for today, University Distinguished Professor Chris Berndt. He is the Professor of Surface Science and Interface Engineering and the Director of the ARC Training Centre for Surface Engineering for Advanced Materials at Swinburne University, also known as SEAM. Chris graduated in 1977 with a Bachelor of Applied Science in Metallurgy. His PhD was earned in Materials Engineering Department of Monash University in mid-1981. His higher doctorate, DEng, was awarded in 2014. He was invited to apply for a position at Stony Brook University in New York, USA in 1989. He was promoted to full professor with tenure in 1995, where he remains an adjunct professor. He has also been appointed to the adjunct staff of the Indian Institute of Technology, ROPAR. He moved to Swinburne University in late 2007 as the founding Professor of Surface Science and Interface Engineering. He was elevated to University Distinguished Professor in March 2014. Chris's professional interests gravitate around manufacturing, especially in the area of protective coatings. He was inducted into the Thermal Spray Hall of Fame in 2007, was the president of the Thermal Spray Society in 2002 through to 2004. He was appointed as a trustee, the board of directors of the American Society of Materials International for 2005 to 2008, and became the vice president of ASM International and progressed to president in October 2011. He's a member of 10 professional societies in the materials and mechanical, manufacturing and bioengineering fields, and is an honorary life member of the Australian Ceramics Society. Chris's major discipline areas are materials engineering and manufacturing engineering, with a subdisciplinary expertise in the topic of ceramics, biomaterials, thick coatings, and thermal spray technology. Chris's presentation today is titled Chaos or Beauty, Microstructure Case Histories in Designing the Face of Matter. Chris, if you're ready, please take it away.
I am in fact ready. Thank you very much for that very kind and far too long introduction, but that's okay. So I'm going to talk about chaos or beauty. The more dramatic slide presented by one of the early career researchers is really dramatic and shows the beauty of microstructures, and hopefully you can see that this presentation will also have some beautiful concepts. I too would like to acknowledge the country. For those of you who are unfamiliar with the Australian system, it is quite often at conferences to have a ceremony whereby gum leaves are burned over a fire and we have smoke in acknowledgement of the First Nations who populated this wonderful continent. I'd like to dedicate this talk to our heroes, the healthcare staff and essential service personnel who have demonstrated their commitment and self-sacrifice. These people are an inspiration to all of us. And remember, we're all stronger when we work together. So let us all thank our heroes. Chaos or beauty? I'm basically going to go through these 5 points. First of all, beauty is in the eye of the beholder. Plato was the first person that said this many years ago, and we only hope that our friends in Greece are coping well with their fires. Here are some beautiful images. I think that everyone would claim that these beautiful images of traditional microstructures Images shown by George van der Wart, and let me quickly go to my pointer. Beautiful images of cast materials, grain structures, different orientations, acicular structures, twin boundaries. Absolutely beautiful microstructures. I don't think there's any doubt. And also I've put down here an advertisement for the combined Australian Material Societies meeting in 2021. We're still moving ahead with that. However, when you look at coatings like this, which are thermal spray coatings, where is the beauty in this? As I was introduced, I was trained as a metallurgist, and if a metallurgist were to look at these structures, they'd be quite surprised that these materials are being used. They'll say there are too many inclusions, there are oxide boundaries. You know, where's the strength? Where's the commonality? Where's the wonderful cast structures or equiax grains that we normally see? So what I'm going to try to describe here is that we really have an ugly duckling here. And I'm going to say that this ugly duckling, that these structures are in fact beautiful. And I will talk more about the features of these microstructures just in a little while. So here are some more structures, for example. This is of chrome nickel fibers in a nickel chrome aluminium silicon matrix. And what you can see is a thermal spray coating. And within that, we have embedded these fibers. This is quite old work, but it shows that thermal spray coatings can create amazing structures. And these amazing structures, in this case, are composites. So why do we use composites? Because they have specific functional properties, increased stiffness and dimensional stability, increased heat distortion temperature, modified dielectric properties, topological response. In other words, by creating these beautiful microstructures, we can also create very interesting properties which can be functionalized for industry. So thermal spray can deposit these composite coatings and freestanding components. And what we think about thermal spray in general is that it's a Swiss Army knife. So there are many processes under the umbrella of thermal spray technology or surface engineering in general. And by picking and choosing the correct tool, we can modify these ugly structures or beautiful structures. So here's another example, a solid oxide fuel cell, all produced by thermal spray technology, where we have a perovskite cathode, a nitrous stabilized zirconia electrode, a nickel nitrous stabilized zirconia anode bottom. And what you can see is we have a material where we've got a composite structure, a dense structure, a porous structure with roughness. And this is just the epoxy embedded. But the point is that we are creating by thermal spray an absolutely wonderful composite on many levels within several layers, and all of these artifacts called porosity, cracks, or composite character, the CERMAT which is created here, for example, they all have specific functionalities which would be very difficult to impossible to form if thermal spray was not around. What you see is what you get. Now, really. So let's go back. So many of you will be familiar with the so-called Ashby maps, but what we've got here is we're plotting the thermal expansion on a logarithmic scale with regards to the thermal conductivity. And here is the material of interest. This is bulk zirconia. So bulk zirconia has a thermal conductivity of about 2 to 3 watts per meter Kelvin. Keep this point in mind, because now if we produce this coating by thermal spray, the watts per meter Kelvin is halved. By conventional thermal spray technology, is halved to 1 watt per meter Kelvin. The thermal expansion stays the same. And you say, so what? What does this really matter? This one data point, this delta lambda in thermal conductivity, has spawned $1 billion industry. Every time that you can fly, if you're allowed to fly, But every time that you switch on the power generator from the grid, you are using a thermal spray coating that employs, that leverages this factor of 2 decrease in thermal conductivity. And now, with more strange materials which are being created now by thermal spray, this number is going down to about 0.6. So what I'm saying here is that these are strange materials because of their beautiful microstructure, and we're changing the intrinsic properties to extrinsic properties. And the extrinsic thermal spray zirconia is now being leveraged to make economic gain. So every time that you use the light switch, think about this graph, because your energy is cheaper and more efficiently produced because of thermal spray. We also have non-equilibrium phases. Now, the way in which we teach engineers is that we have these wonderful phase diagrams, and everything is sweet and everything is reliable, and thermodynamics can be obeyed. However, in thermal spray, we have RSP, rapid solidification processing. So metastable phases, which are non-equilibrium, are common. We get supersaturation effects, changes in crystal structure. For example, we get gamma alumina rather than alpha alumina. We get supersaturation of nickel chrome eutectics. And later on, when I talk about high entropy alloys, you see that there are very interesting structures. So the characterization of these deposits is very challenging. We use many X-ray techniques, neutron diffraction techniques, mechanical testing and corrosion studies. And here is an advertisement for the thermal spray journal, the Journal of Thermal Spray Technology, which does explore all of these features in great detail. So I did say that we'd go back to one of these coatings. So let's look at the bronze coating of copper aluminium. We see a roughened surface. We see splats, which are like pancakes laid on top of each other, or saucers laid on top of each other, or bricks. Embedded grit from the blast media is often observed. It's not bad, you just have to control it. You have the grit blasted substrate. We have cracks which are lamellar. We also, if we look very closely, I'm trying to find cracks which are vertical. Possibly there's one there. We have unmelted particles and we have porosity. So that is the taxonomy. This is how we break up a coating structure. Here's another example of a biomaterial, either hydroxyapatite, or within our lab at Swinburne, Pham, the student, soon to be a doctor, almost Dr. Pham, is creating bagdite coatings in collaboration with the University of Sydney. And again, we see a roughened surface, we see cracks, we see pores, we see splats, and we see unmelted particles on the roughened substrate. So at first sight, you might say that these are ugly, but remember the ugly duckling. These are actually quite beautiful because these are used, at least the ones on HA with hydroxyapatite, these are currently being used on orthopedic implants. And these, which are now being explored with very good results, by the way, will replace eventually, my opinion, these materials called hydroxyapatite. So here's a cartoon. So these coatings are heterogeneous, they're not anisotropic, and that leads to variable properties, which can either be good or bad, depending on the application. But again, I'm pointing to embedded grit blast media. Some places may be overblasted. We see the coating and we see all of these defects. And the coating roughness is typically about 5 to 10 micrometers. We also have the degree of melting. So we have inclusions, oxides, splats, partially melted particles, unmelted particles. And some of the early work by Majewski talks about the theoretical thermophysical models, which give rise to the splitting ratio. Another work, which actually there are many other people, but let me refer to some of the work by Dr. Ang, at Swinburne, we talk about the coverage during the spraying process. So there's a lot of work in the science and the physics of thermal spray coatings. Porosity is of great importance, especially for the thermal barrier example that I gave earlier on concerning erythrostainized zirconia. So we talk about voids. Voids are defined as cracks. They could be vertical, they could be horizontal cracks shown in black. Voids also encompass pores, intralamellar pores and interlamellar pores. So the void distribution is very important, especially for an application which would incorporate a biomaterial application. My computer has frozen for some reason. There we go. So there's a complete picture of the taxonomy of these chaotic microstructures, or ugly microstructures, or strange materials, or, and I'm going to keep on saying, beautiful. Beauty is in the eye of the beholder. So these all begin with splat microstructures. So depending on, and we're looking face down now, we're looking directly onto the substrate, onto the material that you're coating. We could see a cold substrate or a hot substrate. We either get the fragmentation or flower pattern shape, or we get these nice saucer shapes of cracks. If we look at cross sections, we're able to see columnar growth, or we're able to see very, very small grains. So splat. Splat is how we define all of these materials, and it's the combination of many of these splats, layer upon layer upon layer, which give rise to these beautiful coatings. If we look very closely at the interface between a substrate and coating, as shown here and in this area I've indicated, you can see some intermingling. You can see some intermingling, almost diffusion controlled or physical impaction of material of the coating into the substrate. Now, traditionally, I would say that there is no chemical profile across the interface. However, recent evidence with new processes, such as cold spray, has shown that there have been examples where there seems to be a physical interaction at atomic scales across the interface. This is, and also HVOF, by the way, as I should say down the bottom. But the point that I'm getting to is that the interfacial structure refers to the atomic bonding and hence adhesion. Or we could look at composites, and here we have a fibre which is not intended to melt, but the thermal spray material has melted, heat has been conducted away by the fibre, and what we find is oriented growth. But if we do get cracking in these fibres because the heat distortion is too much, that would be bad for this application. And if we get decohesion, that is not necessarily bad because that could lead to increased toughness by strain energy dissipation. So let me give you an interim summary. We're all explorers, as you can see from the Starship Enterprise. Now we have the Starship thermal spray. We've got the scientific area is very fertile. The processing conditions are critical. I'll talk about that in a little while. Control is imprecise, but we're getting a lot better, as I will indicate. They're highly defective. So how do we go from technology to engineering? Let's talk a little bit about the customer. Let's talk about what the customer really wants. And let's remind ourselves that these microstructures are extremely beautiful. So what does the customer want? So this is a very complex chart, and I'm not expecting you to read all of it. But what I'm saying is that from go to woe, from when you set up a torch, there are all of these steps. Bang, 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 bang. And then finally, you can send a product out to your customer. when a customer sees this flowchart, they get very distressed because all they can see is money. They can see manufacturing nightmares. However, how do we go from the physical setup directly to applications? And what I'm basically talking about is, for those who are aware of the valley of death, how do we navigate this bridge from research to commercial application? And that is essentially what the remainder of the talk will be about. So first of all, we have our Swiss Army knife, and now we've got all of these torches. We've got all of these torches, and these torches give us different temperatures and velocities and spray patterns. So we have a cause here, it's the process tool, and then the effect on the coating microstructure. So we have number one, the particle size, that's related to the microstructural sizes of the coating, the velocity, the temperature, the conductivity, the expansion coefficient, standoff distance, cooling rate. So I have many tools as shown in the previous slide. And all of these impact the microstructure. So this is really the science. So many people around the world, many universities are looking at how these process tools affect our beautiful microstructures and give rise to all of these artifacts. So we can now control. We can control the nature of the splat size. We can control oxides, unmelts, cracking, all of these things by correct selection of the equipment, the particle size, and the thermophysics conditions within the plasma effluent. So what I've done quite a few years back actually was look at the microstructural artifact, look at the tool, and look at the outcome. So I'm not going to go through all of these, but let's look at number 5. For an unmelted particle, thermal spray parameters, probably too cold, and you get variable physical properties. For porosity, and these are all keyed, these numbers are all keyed to the microstructural features shown in the previous slides. For porosity, standoff distance, and it changes the modulus of the material. So what we have now is a way of getting to an outcome. So we can now control the outcome by choosing the tool, by understanding the microstructure, the beautiful microstructure. So here we have our torch. Roughly we've got powder injection, in-flight phenomena, and then we got impact with the substrate. And the things that we can control would be feedstock quality, the spray parameters, and the surface prep. And this all happens within a few milliseconds during the spray process. So what we do as sprayers is we go through a troubleshooting decision pathway. And this may seem complex, but all spray shops do this with their spray tables and with their knowledge from the technician. You know, is there a coating? Yes, no. Let's go down, no, check spray parameters, make adjustments, go back to go, check powder, use the right feedstock. Yes, coating adheres, yes, no, and then this is one way in which we can decide how we can get the because sometimes you do have to go back to go. Sometimes you do get into jail. In other words, you need to reconfigure your whole system. Strange microstructures. And I'm going to talk about some materials here. Let me quote Albert Einstein. A ship is always safe at the shore, but that's not what it is built for. Or innovate. No, we've already tried that once, but it didn't work out. So new materials, this is all called risk management because many people are very conservative. First of all, high entropy alloys. These, I predict, will be displacing traditional bond coats very soon. First of all, the attributes, less weight, excellent high temperature properties, low-cost constituents, and the work that I'm going to present has been done in collaboration with IIT Hyderabad and IIT Madras. The students would be Amy Ashok, colleagues would be Dr. Andrew Ang, Professor Murthy. And this book is almost like the Bible of high entropy alloys. I say with a certain element of pride that this manuscript down the bottom can be downloaded. It costs nothing to be downloaded from the Journal of Thermal Spray Technology, and so far it has been downloaded 27 or 28,000 times since May of last year. So this review does actually consolidate much of the information that I'm going to present here in 1 or 2 slides. So the work by Amy within her thesis, she graduated in the recent past, looked at high entropy alloys. These look incredibly messy, or should I say ugly, but they are beautiful. And after a great deal of microscopy and X-ray diffraction and very careful thought, Amy was able to distinguish various phases of different constituents within a high entropy alloy, all arising, and this is just to remind me, all arising due to these features. Let me just check the time here. All arising due to these features that happen within the thermal spray torch. So depending on where the particles and the size of the particles and the alloy constituent, you either get this phase, this phase, this phase, or an oxide. Very interesting. And then if you go into more and more detail, you can plot a map of particle size, small, medium, and large, with regards to temperature, low, medium, and high. And you come up with some quite simple physical models of how we get splat behavior. Whether you've got oxides shown as dark, or you get something which is not oxidized. And I say not oxidized in inverted commas, something which retains mostly the original chemical composition. And that's published in the paper, which is indicated by the DOE down the bottom. Mechanisms of understanding the HEA microstructural evolution. So that's on impact. Now, the full paper also talks about other influences, but the message, the main point, is that these beautiful microstructures have been interrogated and analysed so that we can understand how particle size effects and temperature influence the overall microstructures that are observed by analytical X-ray methods and microscopy. Another example, biomaterials. I mentioned that I'll talk about this earlier on. So the application is very important. It could be a hip, could be a knee, could be a teeth, could be a tooth, could be shoulders, could be a plate. The intention here, though, is to think about strategies for antibacterial coatings, a very hot topic now because of this terrible pandemic. So how do we design a coating so that it could have sharp points, for example, contact killing? How do we design a coating, for example, to be porous so that it could have a biocide that could release over time and kill the bugs? How do we control the surface topography so that bacteria do not adhere? So the outcomes would be improved mechanical properties, enhance the biocompatibility, and possess antimicrobial properties. So we've been working on this as well, and many people have, by the way, not just us. And I mentioned the work from Innovative Bioengineering, the Industrial Transformation Centre, sponsored by the Australian Research Council at University of Sydney. And now I'm going to show the work of Pham, who has been experimenting on both bagdadite and hydroxyapatite. Now, what we see here is a wonderful example of two coatings that physically look different. I think that you can see they look quite different with regards to phase distributions and splat geometry, but the functionality, the intended functionality is identical. That is to be used within the human body on, for example, an artificial device such as a hip or a knee. So we've been measuring the mechanical properties. So bagdadite versus hydroxyapatite versus nanoindentation. Now you may not be able to see these very small indents, but there's a whole raster. Bang, 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 and three of them be circled. They're a lot easier to see with the hydroxyapatite. But all of these nano indents have been applied in a raster across the cross section of a bagdadite coating and a hydroxyapatite coating. And by using software, you're able to carry out, you're able to establish a map of, for example, the modulus, the reduced modulus. And what we find for bagdadite is the modulus is 99 with a variation of plus or minus 19, whereas hydroxyapatite is about 54 and the variation is a lot greater. So the method we're using is extreme property mapping, and there's a series of papers that FAM started publishing in 2019, and there are more recent ones coming out, and there will be others coming out over the coming year. But what we're able to do then is look at the mechanical properties in two dimensions. Is that you're all able to see, also whereas the bagdadite is much more homogeneous. We can also look at how these interact with cells. We have collaboration, as I said, with Innovative Bioengineering, as well as with Dr. Trong at RMIT, just down the road from us in Melbourne. We look at how cells interact on bagdadite versus hydroxyapatite. And we're able to see that the red cells indicated that the red arrows indicate that these cells penetrated into the microstructures of bagdadite and hydroxyapatite, so they are both functional. From that perspective, they allow cells to grow. So the topography is good. We go further, working with colleagues by using our trouble decision pathways. This was all done by FAM, absolutely wonderful work. Measuring a knee that was provided to us from Allegra. Allegra is one of our primary industrial partners who are commercialising a bagdadite. Getting a solid freeform model in the computer, forming the masks which are required for spraying, initially in plastic to make sure that they're okay, then using a metal, making a metal mask, sorry about the stuttering there, making a metal mask via additive manufacturing, putting that over the knee and forming the coating, either hydroxyapatite or bagdadite, where you wish it to be formed, according to what the biomedical engineer tells us. So, improved mechanical properties, better biocompatibility, bone cell proliferation, osseointegration, and with the bagdadite materials possess antibacterial properties. Another topic which I'm going to talk about, 2 or 3 slides, completely different, thermal protection systems. This work has been performed by Bruno Carl, who has recently produced a publication in this area. So the issue here is that we have high flight speeds, Mach 5. We need to conduct the heat as much as possible away from this leading edge. So we have a thermal protection system where we are dealing with high temperature materials, and we need the high thermal conductivity to bleed heat away from the leading edges. The old way, so what some of the early work places zirconium diboride, mullite, and partially stabilized zirconia, all with different functionalities. Now we are focusing on the diborides because these other materials do not quite have the high temperature stability. This would potentially be a good coating for a thermal barrier coating, but for the TPS, what we're talking about is hafnium diboride and zirconium diboride. And we're understanding how these metastable phase equilibria influence the coatings and its properties. Within our lab, we have a very simple cap system, very simple, so that we can produce an inert environment. Because the zirconium diboride is extremely difficult to spray and be retained in its native zirconium diboride. It has a tendency to oxidize severely. So what we've done this is a baseline material on mild steel. There's a hafnium diboride on stainless steel. Again, we carry out the microstructural cross sections, the extreme property mapping. We carry out a probability distribution function analysis via a Weibull, and we determine that there are different families. There are different families of phase constituents composed within this complex microstructure. And we are attempting, by varying the thermal spray conditions, we're attempting to maximize these high hardness regions. So again, let's get back to the theme. These are ugly microstructures. However, the functionality for a TPS is extremely demanding, and the ugly microstructure is proving to be quite successful. I have another 5 slides, Mr. Chairman, I believe. So we're getting towards the end here. So who do we work for? And let's think about the future. First of all, we must understand how these particles interact within the thermal flux. And by taking video images at very high speed, we're able to see that, say, moly particles, and this is old work, but it's still relevant, by Professor Heberlein. What we find is that some particles enter the region, look at A and B, and some particles don't. Some particles miss it, look at C, because the arc is fluctuating at 3 kilohertz. So it's kind of hit or miss. So we're now trying to use different processes that control this process environment. You saw this before, this table. So what we're trying to do is we look at the structure, the process. This is the structure that we want to obtain. We look at the process to obtain a certain property. And now I'm going to try to close the loop by talking about the functionality and applications which give rise to economic gain. So we have this toolbox, the Swiss Army knife. We have a palette of microstructural artifacts that we can use to get these strange microstructures. So here's a traditional approach for thermal spray. Spray and pray. You spray and you pray that something is going to happen, that something is going to stick. You pray that you'll be okay. So we got A at the start, and we get a structure which is C, which is the desirable one. So C, we have a B, we have the bridge. So that's what we're doing, and what many universities and labs around the world are doing. We're trying to make this connection between A and C through this bridge called smart spray. So we're using control feedback loops. We're using the industrial Internet of Things, machine learning, artificial intelligence There's digital twins being created around the world. For example, there's the DSM at Manchester, Digital Surface Manufacturing Network in Europe. We're looking at the science of splats, which we affectionately call splatology. We're using diagnostic devices, and we're gradually looking at feedback control loops. So this bridge called Smart Spray will allow us to get to see the ugly, desirable, beautiful microstructure in a much quicker fashion. So we measure these things. All of these are measured, all of these properties. The powder, the effluent, the offline characteristics of the microstructure, and the properties. These are all varied, they're all variable, and now we're starting to be smart with regards to connecting the dots between the gun parameters and the online parameters and the offline characteristics, ultimately to get the targeted properties. Are we at this stage yet? No. We are almost getting this arrow to connecting this together so that we can get the product that we need all the time. We're almost there. So finally, as I wrap up here, I'd like to also dedicate this talk to many of my mentors in memory of the past. Some of you around the world organise these. And I'd also like to encourage the future generations, and this is just a small subset of the many researchers around the world. They're a small subset in my own local environment in Melbourne. We've got the connection between the past and the future. So what do we know? Final two slides, Mr. Chairman, I believe. We know a lot about technology, not so much about the science. We're still explorers on Starship Enterprise. Discriminate the thermal spray technologies. There are many ways in which we can use this toolkit. Design the microstructure. We have a palette of ways of microstructural features. We need to hit the target, and we need to be smart about it, and digital twinning is one way to do that. So here's my one slide summary. Here's the vision. Right, strange materials create beautiful microstructures. The little ugly duckling there is not so ugly now. We have the vision, we've got the toolkit, we've got the palette, the target, and then finally we've got these building blocks that go to a wonderful application. Final acknowledgement, most important, being supported by SEAM. And here's my final slide, Mr. Chairman. The floor is yours now.
Well, Chris, thank you very much for your talk. I think you've really shown us the beauty of thermal spray coatings. I'd just like to tell the audience, if you have any questions for Chris, please feel free to post them in the Q&A now, and the moderating team will get to those and we'll pass them on to Chris. So Chris, actually to start, I have a couple of questions for you. You probably recognize that I'm very interested in this commercialization idea and taking research into some sort of, industrial application. And you mentioned the valley of death, which is a scary prospect for a lot of people who do research trying to translate that into a product. Is there something, also you mentioned about the smart spraying, which is a very interesting prospect. Is there something that you have seen in your collaborations with people that a lot of people trip over when it comes to crossing that bridge? And is it something that's really, I guess, common, or I guess there's perhaps maybe a mixture of problems that people have when they're trying to cross that valley of death, and maybe even any advice for them?
Yes. One of the most common learnings that a sprayer needs to convey is that the properties of the original material will be different than those of the coating. You cannot just go to your textbook and say the property of this superalloy, the property of this ceramic, the property of this polymer. Hence, I will expect the same physical properties within the coating. That is the first learnings, and once you get over that and say that anything is possible because we can change the properties. So the intrinsic properties are not the same. They are extrinsic properties. The properties of coatings are extrinsic. That is the common jargon that we have. That's one point. The next point is that people think thermal spray is just one process. It isn't. Wire spray, flame spray, high velocity oxygen fuel, plasma, low pressure plasma, liquid thermal spray, da-da-da-da-da-da-da. There are many tools, and all that they're doing is controlling T and V, right, up here in the top left-hand corner. If we control the temperature and velocity, we control C, right? So the B, if those 2 points are understood, you can do anything.
Very good. I have a couple of questions now from the audience. I have one question about your Swiss Army knife. How much would the spray gun Swiss Army knife cost? Would you like to comment on that?
How much does it cost? Fair enough. If you go to eBay, you could probably pick up a flame spray torch for 5,000 US or less. No problems. But it really depends. I'd rather address the question, or you could buy a 2-wire arc system. But here's the other way of addressing the question. How much does it cost to buy a bicycle? If you get a bicycle, it will cost maybe $1,000. But it's all the other stuff. You need the helmet. You need the fancy lycra stuff. You need the shoes. It's exactly the same with thermal spray. You need a thermal spray booth. You need an exhaust system to take care of yourself and your workers and the environment. You need to be able to measure things such as porosity and adhesion. So don't just think about the torch. Don't just think about the equipment. Think about the ancillaries. And a normal factor is, you know, a good spray booth could cost 50,000, right? Minimal. You can do it El Cheapo with a glove box, but it doesn't work. You just melt your glove box. I've done that. I did that during my PhD. You learn that and you don't repeat the mistake. The other question is what costs probably the most is the lifetime costs. And the lifetime cost will be the powder, the feedstock. So the joke I tell my industrial customers is, give me your equipment, but I promise to buy all of your feedstock from you. And because that is where the economic gain is, it's in the feedstock, in my opinion. Thank you.
Yeah, that's it's an interesting comment you say about the ancillaries. I think we're quite fortunate at SEAM that, you know, we have such a sophisticated setup here that a lot of those costs, they're already in the infrastructure here at SEAM. I just want to also pass on a comment from Ruggiero Lima from NRC Canada. He said that thank you very much for an inspiring presentation. It's amazing to see the universes of microstructures we can create via thermal spray, and it's nice to see you in action. I'll also ask you a question. So there's a question from the chat from an anonymous user. How important is training thermal spray expert engineers for the Australian manufacturing industry and its future, and why?
That's almost like a Dorothy Dix question. First of all, training of any engineers in any technology is critical. So I'll be very honest and just broaden the scope. Surface engineering, not just thermal spray, but laser overlays, like what they do at RMIT, for example, and other universities, by the way. Working with industry is important. So first of all, there's the technology with regards to improving the surface, because that's got direct commercial gain. This is where you get to the C structure that I'm pointing to now. That's where you get the growth, because you're more efficient in the mining industry, for example, which is important to the Southern Hemisphere here. So that's critical. But to be quite general, all such training is important, because even if that person goes into sales, or if they change their field, they are much aware of it. You know, some people choose to go into law and be a patent attorney. If they know about this engineering aspect called surface engineering, they open up their prospects with regards to their own sustainability, you know, their own livelihood. Medical doctors, they may wish to know about these coatings for their own purposes. So I've wandered around a little bit about that question. I should thank Rogerio for keeping up as well. Thanks for keeping up. It's probably late in Canada. I don't know whether you want to narrow me down just a little bit more, Thomas. I may have wandered around too much.
No, I think that's good. We've got quite a few questions from the audience. If the audience has any more questions, please feel free to send them through. But no, thank you very much. There's a question from Rosalie. She says, when high entropy alloys oxidize or corrode, do you see any differentiation of corrosion products, and is it useful? Do you have any comments about that?
I'm trying to get to the slide quickly. One comment is, first of all, thank you, Rosalie. With regards to the corrosion studies, I think we're talking about one of these pictures here. All right. So in other words, we are going to get galvanic effects, assuredly, because these are all different phases, all different structures. Porosity is not too good, by the way, for corrosion studies. One of the, it's not a secret, but what people don't realise is that many of the coatings which are used for corrosion protection are also impregnated with epoxies. So there's usually, if there's porosity and the intention is to use it in a wet corrosion atmosphere, then epoxy will fill up all of the pores and give protection with high temperature corrosion. So the intended application is 800 degrees centigrade plus. And what we're trying to do here is we're trying to stabilize these high entropy materials here. We're trying to avoid the oxides, trying to stabilize these materials because they've got good high temperature stability compared to, you know, compared to the materials which only have 3 elements or 4 elements. So to answer your question, yes, there is a great deal of electrochemical cell setup for wet corrosion, but for high entropy alloys, the intended application is for bond coats, for thermal barrier coatings, where the corrosion mechanism is more like high temperature oxidation. Thank you. Thank you,
Chris. I just want to make a comment. It's up to you, but I know that sometimes if you switch your video off, it may help with the bandwidth issue. We're getting most of what you're saying through, actually. It's not a huge problem, but I just thought I'd make a comment in case if you wanted to turn your video off, because I think a lot of people.
I thought my video was off.
So, I think it actually might be. My apologies.
Yeah.
So there's another question from the audience. It says, do you think innovation within thermal spray processing has become a little bit stagnant in terms of the actual processing? And do you think a lot of the innovation comes from new materials. What do you have any comments on that?
It's definitely not stagnant. If you could see me in my office, you could see me jumping up and down. It is not stagnant. And if you believe that it is stagnant, and if you're in the Melbourne area, visit us and you will see the activity, or read the Journal of Thermal Spray Technology and interrogate that, and you see that it's not stagnant by any means. Feedstocks, I'll try to speak a little bit more slower to get around the bandwidth issue. So for feedstock issues, what is happening is absolutely incredible. It's absolutely amazing, because we're now no longer restricted to solid feedstocks. We are able to use liquid feedstocks. And this has happened most recently over the last decade. It's actually been happening in the background for 25 years. But the progress with liquid feedstocks is incredible. And behind the scenes, you know, look at the patent literature, and you'll see that there's a lot of new stuff being done with liquid feedstocks for thermal spray. I predict that liquid thermal spray, which is done under ambient conditions, is going to compete with CVD and PVD under vacuum conditions. And when that occurs, it means that you'll be able to apply a thin coating on a large turbine blade, which is 2 meters long, with ease, with relative ease, or on other very large components. The excitement with regards to thermal spray and feedstock is undiminished. The progress, it's just incredible what's happening. And what's happening in the near future is going to be even more incredible. We're on the Starship Enterprise. No boundaries.
Fantastic. I think that's perfect spot actually to finish. I feel like it sounds very promising, and like Chris said, you know, perhaps visiting SEAM and seeing what's going on here. Chris has done a great job at demonstrating what's some of the work that's happening at SEAM. There's very beautiful images and fantastic results. So on that, I will wrap up today's webinar session because we're.
Can I have one comment?
Yes, please, Chris, if you do.
Our partners, RMIT and UniSA, are part of SEAM, and you know, you're more than welcome. Well, I'm going to throw into the thick of it and say you're more than welcome to visit Colin and Christy at UniSA, and the Milan, Mar, and Ivan, and others at RMIT. So, sorry about doing that, colleagues, but SEAM is 3 universities and many industries. Sorry to interrupt you, Thomas, but I want to make sure that our friends are included.
Absolutely. No, absolutely. So yeah, without further ado, I'd just like to thank Chris very much for the presentation today and for fielding those questions. Thank you very much to the audience for submitting those questions. If you have any questions that I either didn't get to, I'll pass them on to Chris. But also, if you'd like to reach out to him and have a chat, I know Chris is very, he likes to foster collaboration and education. So that opportunity is there for you. I also just wanted to remind people about the next SEAM event, which is happening next Thursday on August 19. It's going to be a panel session with industry partner Jeff Lang from Titomic Limited, chaired by Swinburne Professor Alan Duffy. And the title is Victoria's Manufacturing Industry in a Post-COVID World. Set to be very interesting. Please come along to that. Apart from that, thank you very much for attending today, and enjoy your days.